So hello everybody, I'm Paul Sobey. I'm head of product for StorageOS. I'm here with my colleague Ferran Castell, and we are going to demonstrate the use of the database as a service pattern within Kubernetes. So what we'd like to do here is compare and contrast traditional models of deploying databases with the new and exciting patterns that are afforded to us by running our workloads within Kubernetes and allowing the orchestrator and StorageOS to help us out. So if we think a little bit about a traditional model, well, first of all, it's very server-centric. We need to install that server, we need to tend that server, perhaps present some storage to it. We need to install our applications, monitoring, and so on and so forth. So quite a server-centric view of the world. Secondly, if we want to scale that environment, we need to scale it vertically. If we want to make our database server bigger, we really have few options. We add CPU, we can add memory, we can add disk, and so on. Vertical scaling reaches a point where it can be challenging. Horizontal scaling is certainly to be preferred. And thirdly, all of the servers and services in the enterprise, database machines typically behave the most like pets. These are the servers that are tended in the corner, carefully tended by teams of DBAs. So they really function more like pets than cattle. And of course, in a cloud-native world, increasingly the trend is to try and treat servers more and more like cattle, rather than individual units. The fourth point we'd like to make is that, of course, in the traditional environment, there's a degree of imperative setup there. Even with declarative configuration management, we've still got lots of imperative steps in order to stand that server up, set up the appropriate monitoring and so on, and drive the actual database, create the databases and so on. So all of this stands in stark contrast to the cloud-native world which Kubernetes and StorageOS enables. First of all, we're less server-centric. Now we start to think about being application-centric. So storage should just be one more property of an application. The interesting thing here is the application. And that's really how we at StorageOS think of the world. Secondly, we should be able to scale horizontally. So typically we have a database server, it contains many databases, it's been carefully tuned and so on and so forth. But Kubernetes opens up these whole new patterns where rather than having a single database server or several highly tuned instances, we can simply represent each database as an individual pod distributed around the cluster. So this buys us some horizontal scaling for free of our workload. Of course, we want to be able to think about our individual nodes as cattle. Even running configuration management on nodes should begin to become an anti-pattern. We'd like those nodes all just to be throwaway. And of course, declarative. So we can really leverage the orchestrator here to do a lot of our work for us. So we declare the way we want the world to be, and we allow the orchestrator, both Kubernetes and the StorageOS control plane, to converge the world to our desired state, and indeed to self-heal if that state diverges. That brings us to what we want to show you today. What we have here, external to our Kubernetes cluster, is a Postgres server. And it's got several databases on it, around 10, I think. What we're going to do in this demo, what Ferran is going to do, is we're going to extract all of the data from those 10 databases, and we're going to turn that into 10 individual or several individual pods distributed around our Kubernetes cluster. So we've moved from that sort of tended database server to simply migrating workloads as just one more workload within our Kubernetes cluster. And with that being said, over to you, Ferran.
Thank you, Paul. Thank you for the introduction. And to clarify why we want to do that and why we want to explore the possibility to run databases. In this case, we're going to use a relational traditional database, a Postgres, to run from a standard or traditional database model towards containerized solution. But not only to run the database itself as a container, that actually is not that difficult, is how easy it is to move from one to the other in a matter of minutes and leveraging the orchestrator, in this case Kubernetes, and the storage system, so StorageOS, to have a production-grade style of database. We're talking about high availability, we're talking about dynamic provisioning, etc., etc. So let's go into it. My name is Ferran Arau. I'm an engineer at StorageOS, and we are going to try to show you a bit of a new paradigm of how to run databases. This new paradigm might be suitable for specific use cases or others, but the idea is that we are not restricted to one big server with many, many databases. There are different ideas that we can explore here, but we're no longer restricted to one model. So let's explore a different one. We're going to run from one big database towards a lot of either smaller or independent instances of Postgres running on Kubernetes. To give you a bit of context, what do we have? Have a Kubernetes cluster with one master and 5 workers. You might have seen that one of them is Cordon. We will use that later on when we shoot things, 2 live demos, and we're going to shoot things. It's going to be fun. And then we're gonna use this node to do some other operations. So let's have a look. StorageOS is already installed. As StorageOS installs different components, but the main component is the daemon set. That daemon set is an instance of a StorageOS container running on every node, or in this case, on every worker of my cluster. Just to give you an idea, an overview. First, StorageOS is running a daemon set. We have one daemon set instance, so one pod of a StorageOS per node. And we have the other components that are part of the StorageOS as well, the CSI helper that some of you might be aware of how it pans out with Kubernetes, and a few other components that we can talk across the demo. Now, StorageOS is installed. When we have that installed, StorageOS creates that mesh that becomes a cluster rather than having independent pods, and we can access the StorageOS user interface. So this here in my browser is the access to that StorageOS interface on that specific cluster. What we can see here is that we have the 5 worker nodes already going together. So this is a bit small, the font, just to give you an overview. So from now on, we're going to go a bit in detail. Aside of the Kubernetes cluster, as Paul described before, we have a Postgres database. One instance of Postgres with 10 databases that could simulate this traditional environment where you have many, many databases in one instance. That instance might be taken care, might have a lot of backups, might have high availability through active-passive models, etc. But how many times have you seen yourself on a situation of having to touch, scale, migrate, or operate that instance of a relational database? It becomes a big challenge for availability and for operability. So what we're going to do is translate these 10 databases that I created just for clarity with numbers so we can see where they land, that have just random data from pgbench, and we will create one namespace for every database. So we will create one microservice style architecture where we can run our instance of Postgres for each application that we're running. If this model, you think, oh, maybe microservices here is good, but it has overhead of running the instance, we think that this is just an example. We have a model where we can now segment our namespaces based on our business model, our teams model, maybe our environments, whether it's staging or development or different development teams. So rather than having one big instance and having a challenge also to tune based on the profiles of access to that database, we're going to have independent instances. And those independent instances can be tuned independently. So let's connect to one of them and let's have a look. We have a few random tables to give you a bit of an idea of what we have here. This comes from pgbench. It's just random data for benchmarking to generate that I use to generate randomized data. Great. Now, what do I have? I have namespaces for every application. So we have app 0 to app 9, so 10 namespaces here. And let's first install the Postgres instances for every single one of these namespaces. I'm going to use stateful sets today, and I'm going to use quite a low-level stateful set. Here, if you're not completely familiar with the stateful set or with the specifics of Kubernetes, it's fine. We will see from an overview point of view what that actually means. So first of all, let me show you how that stateful set looks like. It's just a Kubernetes controller that will enforce, from a declarative point of view, that we have one instance running of our database. So we have that container running. That container, it's going to run a fairly standard Postgres image, and we're going to use a mount to PG data. Obviously here you can, because this is declarative, we can add specific tuning. We can say, for instance, our transactional log can go to different partition or a different volume, etc. So here we are defining a template. It's a standard Kubernetes YAML, but in the end, what we're doing is following an application-centric model where we have a database or an application in this case that requires capacity. And it not only requires capacity, it doesn't want to have to provision that capacity to mount, to attach, or to bring from a cabin of disks that capacity to an OS and to a file system. It just wants a capacity. It just wants a volume. And we will do this through CSI. So in between Kubernetes and StorageOS, we will have these interactions, all API-based, that will allow us to provision that capacity. We're going to use the StorageOS replicated storage class that will enforce replication. We will see that later on. But we can have multiple storage classes. So here, I will enforce, by definition, at least one replica, one synchronous replica of that specific volume. So we will have mapping one-to-one application to volume. So let's go for every single one of them and create these YAMLs. Let's make sure that we have, for instance, our databases loaded. So what I'm doing here is just an iteration of loop, a tiny loop that goes and applies the same YAML for 10 different namespaces. Obviously, this is something that you could do from a CI/CD point of view, or your teams could do from a CI/CD point of view. But I want to show you the low level of how easy it's actually to do this. Now, we have created these stateful sets. What actually do we have? So for all namespaces, every single pod that runs Postgres. So we can see that for every namespace, we just simply have one instance of a database. And that maps one-to-one to the persistent volume claims. Smaller. So we have one persistent volume claim that maps one-to-one to those applications. Now, StorageOS dynamically provisions the persistent volume, and this automatically translates into StorageOS volumes. Now, StorageOS maps one-to-one the namespaces for those that have persistent volume claims created. So let's take an example of app 3, for instance. So on the StorageOS user interface, we can see that the primary of that volume landed on worker 1, while the replica landed on worker 2. So first column is the master, second column is the replica. Let's go have a look at the specific of the volumes. We have the volume, that's the PV that is dynamically provisioned, that's the StorageOS volume, and we can see that the application is running in worker 1, while the data is also allocated in worker 1. That means that we have low latency, and this is achieved through the StorageOS scheduler. One of the components that we installed initially was that the scheduler, or an extension of a Kubernetes scheduler, that tells Kubernetes if you can put the pod along its data. So we can have low latency, fast performance. As I mentioned before, we have a replication target of 1. And what that translates to is into the instance of the data running in worker 1 or being stored in worker 1, we aggregate the capacity from those backend nodes, those nodes from Kubernetes. We're taking those disks and saving the data there. And at the same time, we are replicating synchronously to worker 2. So one replica or one instance of the data goes to one specific node or another. The unit of failure here could be a node. Let's go and do the migration. How do we do that? We're going to create a service, an external service that points to that instance of Postgres that is running outside of the cluster. it's just a simple service to use the DNS names and leverage the DNS capacity and the networking self-discovery of Kubernetes along an IP that is specifically defined, is a bit bigger, is specifically hard-coded to that database. Once we have that endpoint created, we just created a service, we can reference that service to say the source of our data will come from that specific URL. Now, how am I going to do that, or how we can do that on from a Kubernetes point of view is via job. So simply, we will run a pgdump that will do pgdump from that big instance, that production instance, towards the destination, which is every application that runs on a different namespace. And we will run one of these jobs for every namespace. We're using environmental variables here, so information comes from a config map. Of course, this is, once again, something you want to do from a CI/CD point of view, but I want to show you the bare bones of how we can do that. Of course, for production, you wouldn't pipe backup output towards a restore towards the restore input, because that for production could cause trouble. You could have an intermediate solution here from backups at night or a migration specific time in the day to do this, this migration of data. So to have a look at the config map, we use the same source, that service, that external service that we created, and the destination, thanks to the Kubernetes primitives, we can use the same name, pod name, because we use a stateful set, the name of the service, and the namespace. So we can reference the same name pointing to different DNSs, pointing to different instances of Postgres just because we are using Kubernetes and namespaces. And you can see that the application will need to change its name, so we will patch this, this config map. So let's create the config map. Once again, I'm iterating over all of them and creating a config map. We're gonna make sure that the application itself changes on the config map. You can do this from a patch, from your CI/CD, using templating like Kustomize or using Helm. So simply have a list of your databases and make sure that the config maps reference them. So if I, for instance, take one of the applications and I get the config map, we will see that it's pointing to that specific one. So in this case, we have app3 pointing to the database app3, and only that one. Of course, the credentials here are a bad practice. This is just for the demo. You could use secrets, etc. So let's go and create the job. So what we did here is create actually 10 jobs. For every single instance of Postgres, so for every application that we have one instance of that job. So let's have a look. And we can see the output of that PG restore saying, okay, the data is there. Because there is not much data, there are maybe a couple of 100 megabytes. The migration is fairly isolated, but it's fairly fast. So in a matter of minutes, we have, I'm going to show you this again. We have a system that has migrated data from a production database to automatically deployed instances of database, and those instances of database are backed up by StorageOS. So actually, let's go and have a look. So getting in the specific container, I'm just taking app3, for instance, and going inside that container where Postgres is running. Let's go have a look of the disks that are mounted in there. So we can see the operating file system is usually mounted normally from a container. But if I go to where we actually mounted the Postgres mount point, we will see that we have a StorageOS volume. So in PG data, here we are. We can see the specific disk. And that disk is a StorageOS created device, standard POSIX Linux device that mounts into a mount point inside the container. The data in there is backed up by StorageOS, regardless of that data being on the same node as this Postgres instance or not. To recap a bit, Paul can give us a bit of the recap on that demonstration, how we migrated those databases from a big instance to a containerized solution in a matter of 5 to 10 minutes.
Thank you very much, Ferran. That was fantastic. So, yeah, guys, just to wrap up quickly with this, what we wanted to try and express here is just how easy it is to migrate data from an external database into Kubernetes. So first of all, we've taken a server and we've moved all that data. Second of all, we wanted to highlight that the application-centric model makes it very easy for us to deploy new databases. This is such an easy thing to do in Kubernetes. We've just done it in a matter of minutes. And thirdly, we wanted to really emphasize that scale horizontally pattern. It's very easy for us to take a database server with lots of databases on it and turn those into individual pods. We've got some really increased operational flexibility there.